Let us see now how to import an image and how to extract some of its basic features. To do so, I import the imread function, which is to import a figure, and I also import subplots for displaying the picture. So I assign a variable name, which I use here as Serep, and I use imread to access the figure, which is in a subfolder called figs, and its name is cerebellum.png. So once it's imported, I can use subplots to display it, and it's the best if I specify a figure size that is not the default, and I can say something like, I don't know, 12.8, and then I can display my image using imshow. The easiest if I just use the variable name. Let's see what happens if I just display the image in this way. So strangely, the image background is yellow and the image itself is mostly greenish or blue. So that is because matplotlib, which is used here, has applied a default color map. I haven't specified a color map. So if I want that to be different, I need to specify a different color map. And because I took this image from Wikipedia, from the entry for Cerebellum, and there it's a black and white image. So let me specify the color map as gray, Gray. And if I do so with that small change, it's actually the original black and white figure. So that's a good way, of course, and the important thing is now that we want to access features of that figure, we need to see what it is. So what we can do is we can specify the type of Serep, and it turns out it's a NumPy array, which is nice because it also means that we can apply all the functionality that we know from NumPy. So for example, we can check its shape, and we see 224 by 444 entries. So this specifies the image dimensions. If you look back at the figure, it's 224 rows and 440 columns. Now, if we have a NumPy array, it also means we can slice it like a NumPy array. So if I just copy that code from above and display it here, I can use NumPy slicing. Like for example, if we want to see the central area here, which is located around 100 in rows and 230 in columns approximately, we can do so by going from 80 to 120, around 100, and in terms of columns, going from, I don't know, 200 to 260, so around 240. And if you use that same code to show this, we have a zoom of the original figure, which zooms into that central part. If we just go above, we're somewhere here in that area where the cursor is now, that central black structure. And so that's a very nice feature, because now it means it's very easy to manipulate all the data that in there. One thing that we haven't done, but that we can do so now, is we can actually take that slice of NumPy out and just display the numbers that are in there. So just to have a feel for what type of numbers does that image variable contain, and we can see that these numbers are all floating point. It says down here floating point, and the numbers are all between 0 and 1. And the reason that is because in images the intensity for each pixel or each dot on that image is specified as a number between 0 and 1, where 0 means black and 1 means white. So all those numbers are intermediate between 0 and 1 to specify different levels of gray. They are intensities. And now that we know the shape of the array, and also we can see that there are numbers distributed between 0 and 1, a natural question to investigate would be, how can we draw a histogram of the data that is there so that we can see the distribution of the gray values? So let's try to do that. So for a histogram we need to create a plot, and we create a plot of fixed size, say 10 by 6, and then we can access it with not imshow but with hist for histogram, and we can just try to apply the histogram on that NumPy array that we have. And what you can see, the first thing is it takes quite a long time to show up, and then it brings up a weird image with several of these distributions and all sorts of colors, which is a bit unexpected, but it can be explained if you look that actually it's been displaying 440 containers. And so what it means is that the hist function has tried to do many histograms for either columns or rows of that image, and that produced that strange picture. So what we need to do is, before we apply to the NumPy array, we have to specify that we want only that we want all the values of the NumPy array. And to do so, we can use a function called revel, which puts all those values into one long array, which has as many rows as there are values in the whole image. And the second thing that we can do, of course, bins. Bins is specified, so these are 10 blocks of colored bars because we have a default bin size of 10. And if we want that to be different, so we have on the order of 100,000 pixels here, we can easily take like 100 bins. So if we do that, we get an image that looks a little bit more like the single histogram that we expected. It's still not quite nice. So we have a histogram which we can't really see because there's one column that goes up to on the order of 50,000. So it means there are 50,000 values that are on the order of 1. Why would that be? Well, if we go back to that original image and we remember that 1 represents white, this is of course the background. So it's a bit of a trivial information for us. We don't really want to see that. I suppress that matplotlib output below by using a semicolon here. But what we can do is we can try to filter that image or the image array by such that we can take out all the values that are 1 or nearly 1, and to get rid of this big thing that represents the background. So what we can do is we can put on that Sareb array, we could put a condition such that we can say, sorry, that needs to go inside, take all elements of that array, but only where this array is less than 1. And then do the revel, sort of put it in one long array and make the histogram. So it gets better, but we still have loads of values near 1, and the reason is they maybe are not exactly 1 but slightly below it. So if we just adjust it a little bit more and we say take everything that's less than 0.96, then we finally, by this artificial cut at 0.96, which is the point here, you can see everything else cut off, we can see that broad distribution in the center of those intensity values, and we can now see a better representation of that histogram. And we can see there's a number of sharp bins with larger values, and that has to do with the stripiness of the original image. But you can zoom in more, you can say take 1,000 bins, and then you will get a much finer resolution of the actual values that are contained here. And you can see that from this image that these are genuine values. It's not because these values are in a certain step size, as you might suspect from seeing gaps.